This is Module 2, our second lesson in Algebraic Review. We'll explore functions, their graphs, various properties, slopes, average rate of change, and practical applications. Remember, these topics aren't isolated, they're stepping stones into calculus. In computer programming, a function is a named set of instructions that achieves a specific outcome. In mathematics, a function serves a similar purpose. It is a named procedure that performs certain calculations. A function takes an input, processes it according to a set of rules or operations, and produces an output. Consider an example. We have f of x equals 1/2 x minus 1, and we wish to find f of negative 4. Now to do this, all we're really trying to find is what is the y value when x is equal to negative 4. So we will take negative 4 and plug it back into x in our function to get that y value. Looks like we have f of negative 4 is equal to 1/2 times negative 4 minus 1. Well, now that gives us, let's see, 1/2 times negative 4 is negative 2. Subtract 1 from that, looks like our y value here is negative 3. And so we have f of negative 4 equals negative 3. Now what this means is that when x is negative 4, y is negative 3. So on the graph, we have the point negative 4, negative 3, which looks something like right about here. Now let's extend this concept. Okay, in this problem, we have f of x equals negative x squared plus 3, and we want to know what would the y value be for an input that is h units away from x. Well, x in this case is just some generic value. I'm going to go over here and just label it, and I'm just going to say, okay, well, this value right here is x. Now, if I had an actual number for that, I could put that number back into the function and get a number for the y value. Right now, just generically, I know that I've got a point up here where the x value is x, and the y value is f of x. And so what happens if we go h units over from that? So I'm going to move over here some amount, and this would be h units, which will give me a new value, x plus h. And on the graph, I would have a point up here. The x-coordinate would be x plus h, and the y-coordinate would be f of x plus h. So the question here is, well, what is that y value? Well, okay, f of x plus h, we can go over here and we can evaluate that. That just means that we take x plus h and we put it into our function up here. So we have negative x plus h quantity squared plus 3. That's the y value. And we could just leave it like that, or we could go in here and simplify this a little bit. Let's see, if I multiply this out, I get x plus h squared, which would give me x squared plus 2xh plus h squared. And distributing this negative inside here, I would get negative x squared minus 2xh minus h squared plus 3. And that's what that y value would be. Now it's worth noting here that if I knew exactly what the value of x is, if I had a value for that, I could of course go over here and put that in here and get something for that. And if I knew what h is, if I knew I was going over, say, 2 units, if h was 2, then I could plug 2 into the h over here, and I would know exactly what that y value is. In this case, we're doing this in a very general way, and so we get an expression here that involves both x and h. Okay, now I'm going to click over into Desmos to take a look at several different classes of functions. A constant function is in the form f of x equals some number. The graph here is a horizontal line. Let's consider a linear function. The graph of f of x equals x is a line going through the origin with slope 1. The graph of f of x equals x squared is a parabola. Consider the graph of f of x equals x cubed, which is a cubic function. The graph of f of x equals the square root of x starts at the origin and then goes up and to the right. An exponential function in the form of f of x equals e to the x is often used to model population growth. Logarithmic functions have the property of growing quickly at first, but then leveling off. Now let's consider a general function in the form g of x equals a times f of x plus b plus the constant c. In this case, we're starting off with f of x equals x cubed, the cubic function. Note the effect of changing the value of a. A adjusts the scale of the function. When a is negative, it reflects the function across the x-axis. When we change the value of b, it shifts the function left or right. When we change c, it shifts the function up and down. So in each of these types of graphs that we've seen here, we can generalize them by rewriting the function as g of x equals a times f of x plus b plus c, and then modifying the values of a, b, and c. We're going to focus on linear functions for a bit. A linear function is one that can be written in the form f of x equals mx plus b. Here, m is the slope and b is the y-intercept. Consider an example. In this example, we want to find the slope and y-intercept of 6x minus 2y equals 14. And we've seen that if we can write this in the form y equals mx plus b, then we can read straight from there the slope and the intercept. So let's see if we can rewrite this function in the form y equals mx plus b. I start with 6x minus 2y equals 14, and I think I'm going to just drag this 6x to the other side of the equal sign, which will end up giving me negative 2y equals negative 6x plus 14. If I divide both sides by negative 2, that will isolate the y on the left-hand side, so that will give me y equals negative 6 divided by negative 2. That gives me a 3x, and 14 divided by negative 2 gives me negative 7. And straight from here, I can see that this is in the form y equals mx plus b, where m is equal to 3 and b is equal to negative 7. The slope is 3, the y-intercept is negative 7. The slope indicates the line's steepness, with positive slopes rising and negative slopes descending. Horizontal lines have a zero slope. To find the slopes between points x1, y1 and x2, y2 on a line, divide the change in y values, which we sometimes call the rise, by the change in y values, which we sometimes call the run. This gives us rise over run, which is y2 minus y1 divided by the quantity x2 minus x1. This represents the rate of change in the y values relative to the x values. Now let's look at some examples. In this example, we want to find and interpret the slope of the line that passes through the points 2, 0, and 5, 4. So I'm going to go over here. I'm going to start by labeling my points. I'm going to say that 2, 0 are x1 and y1, and 5, 4 will be x2, y2. Now this is somewhat arbitrary. I could call it the other way around, but let's just move forward with this. So the slope I know is going to be the difference of y values over the difference of x values. And it looks like that's going to give me 4 minus 0 over 5 minus 2. Well, that gives me 4/3. So I'll have a slope of 4/3. Now let's remember what this means. It means that if x changes by 3 units, then I can expect for y to change by 4 units. Let's apply this idea of interpreting the slope to real-world contexts. The cost of a rental car is $25 per day, plus a flat rate of $40. If the car is rented for X days, then the total cost of the rental may be expressed as y equals 25x plus 40. We want to interpret the slope here. Well, we see we've got a linear function in the form y equals mx plus b. In this case, m is equal to 25. Now, what does 25 mean in this case? Let's think about what y means. Y is the total cost, and x here represents days. And so m equals 25 just means that the total cost is increasing by $25 every time the day increases by 1. In other words, the cost is $25 per day. Now in this case, that was given to us as part of the problem. But even if it wasn't, and all we had here was the equation, we could have come up with that information. In this example, the retail value of a new car after X months is given by Y equals $32,500 minus $110X dollars. We want to interpret the slope. Well, how about we just start off by finding the slope? I'm going to rewrite this as negative 110X plus 32,500, which is in the form mx plus b. And we can see here then that m is equal to negative 110. So we've got a slope of negative 110. Now what does this mean? Well, we know here that y is the retail value and x is the number of months. And so what this means is that the retail value goes down by $110 every month. We have seen that with linear functions, the rate of change is constant and is represented by the slope of the line. The rate of change for most functions is not constant. Consider a function that represents the cost in thousands of producing X hundred pieces of computer equipment. Because we don't have a constant slope, we approximate by analyzing the slope over a selected interval of x values. For the sake of illustration, consider the interval between x equals 0 and x equals 1. Now we don't know exactly what the slope of this line is, but we can see that it is steeper than the line between x equals 1 and x equals 2. We are examining the average rate of change here. So the average rate of the cost in thousands of producing the computer equipment is greater between 0 and 1 than it is between 1 and 2. This makes sense because of factors like the initial setup of production lines and learning curve inefficiencies. Given a function f of x, the average rate of change from x1 to x2 is given by the quantity f of x2 minus f of x1 divided by the quantity x2 minus x1. Let's explore this with an example. Bubble sort is a simple algorithm that is used to sort an array of elements. It works by comparing each element with every other element. If an array has n elements, the number of comparisons made is f of n equals 1/2 times n squared minus n. We want to find the average rate of change in comparisons if an array with 10 elements is replaced by an array with 20 elements. So I know the average rate of change will be given by the formula f of n2 minus f of n1 in the numerator over n2 minus n1 in the denominator. So I'm going to make myself a little table over here. I'm going to have my n values, which are acting like x values in this problem, and I'll also have my f of n values. So I know that n goes from 10 to 20, and so my y values here will be f of 10, which will be 1/2 10 squared minus 10. So we get 1/2 10 squared minus 10. And let's see, that would be 100 minus 10, that's 90. Divide that by 2, we get 45 as that y value. And f of 20 would be 1/2 20 squared minus 20. I'm just putting the 20 in place of n up here. So that's 400 minus 20 gives me 380. Divided by 2, that would give me 190. And so I have my two n values and I have my two y values that go along with that. And so it looks like in this case, my average rate of change will be 190 minus 45 divided by 20 minus 10. And let's see, 190 minus 45 will give me 145. And in the denominator, I have 10. It looks like that would equal 14.5. So if the number of elements go from 10 to 20, I can expect the number of comparisons to change by an average of 14.5. In this last example, we found that the average rate of change in comparisons between n equals 10 elements in an array and n equals 20 elements was 14.5. Of course, if we were to consider the rate of change over a different interval, say from n equals 0 to n equals 10, then the average rate of change differs too. A ball is thrown into the air. The ball's height after t seconds is h of t equals negative 16t squared plus 32t plus 6.8 feet. We want to know what is the average velocity of the ball between t equals 1 second and t equals 2 seconds. Well, the average velocity will be h of 2 minus h of 1 over 2 minus 1. Now we can throw these values into the calculator and find that h of 2 is 6.8, and h of 1 is 22.8, and of course in the denominator we just get 1, and this gives us a negative 16. So the average velocity between t equals 1 second and 2 seconds is negative 16 feet per second. In the last example, we found that the average velocity of the ball between t equals 1 second and t equals 2 seconds is negative 16 feet per second. The velocity is negative here, which indicates that the ball is descending. Consider, for instance, if we were to look at the average velocity between, say, t equals 0.5 seconds and t equals 1.1 seconds. Note how the slope of the line is positive. The average velocity here is 6.4 seconds, indicating that the ball is ascending. Lastly, let's consider the average rate of change between t equals 0.9 seconds and t equals 1.1 seconds. We see that the average velocity is 0. That is, the ball over this short interval at the top is, on average, not moving. Now this shouldn't be a surprise. Think about what happens when you throw an object in the air. It goes up, hits a maximum point, and then it goes down. At that instant, where it switches from going up to going down, it's not moving. Now when we consider the ball at that moment, we are subtly transitioning from thinking about average rates of change to an instantaneous rate of change. In other words, we just snuck into the world of calculus, where we stop thinking about changes over an interval and we start thinking about changes that happen at a specific point. Now we are a few lessons away from being able to compute instantaneous rates of change, but that's where we're heading, and when we arrive, you'll be equipped with the tools to tackle a whole new set of problems.